There are a few observations you can make about this problem fairly quickly. One thing you can observe is that the only way to remove frogs from the game is by jumping, and a jump removes 2 frogs. So if you want to end up with 1 frog, you'd best start with an odd number. So if even n is even, that's just never going to work. It's never going to be possible to end up with 1 frog. Another easy observation is that if you start with just 1 frog, then of course it's possible to end up with just 1 frog. You do nothing. So the case n is 1 definitely works. Also, quite quick to observe, is that if n is 3, if you start with 3 frogs in a line, then 1 single jump will leave you with just 1 frog left. So the cases n is 1 and n is 3 are both possible. So here we see the case where n is 5. If we have 5 frogs, the natural thing to do is to start by taking the frog on lily pad number 3 and letting it jump to the right. Now, the problem with doing this is it leaves us with frogs on lily pads number 2 and 6, and those are both 2 more than a multiple of 4. And if we swim around with those frogs, they'll stay on numbers that are 2 more than a multiple of 4, and it's very hard to see how we could possibly line them up for another jump. There are other ways we could start. We could start by doing some swimming instead, but if we play around, we certainly reach the conclusion that 5 is probably not possible. And similarly, if we play around with n is 7, we reach the conclusion that that's probably not possible either. So we should try to prove that 5 and 7 are not possible. Here, however, is the case of 9 frogs, and it turns out there's something interesting we can do when n is 9. So if we do the following sequence of moves, we first let the frog on lily pad 7 jump to the right, then we let the frog on lily pad 4 jump to the right, then we let the frog on lily pad number 10 swim to the left, and then we let the frog on lily pad number 1 swim to the right, then we let the frog on lily pad number 7 jump to the left, then we let the frog on lily pad number 4 jump to the left. Now we end up with just 1 frog, and even better, it's on lily pad number 1. We didn't use anything off to the left of the board, and we only used the vacant lily pad number 10 on the right. So what this tells us is that if we've got any number of frogs from 9 up to 999, we can use this technique to remove 8 frogs from the situation. So this is usable in an inductive proof. If we know that n is possible, we know that n plus 8 is possible too. This tells us that all numbers of the form 8k plus 1 and 8k plus 3 are possible, provided they're in range, of course, not more than 1,000. Now we want to try to prove that the remaining cases, which are 8k plus 5 and 8k plus 7, are impossible. One way of going about this is to consider the number of frogs that are on lily pads that are a multiple of 4, the number that are on lily pads that are 1 more than a multiple of 4, the number on lily pads that are 2 more than a multiple of 4, and the number on lily pads that are 3 more than a multiple of 4. Why is this sensible? Well, swimming keeps the frogs in those classes. So if a frog's on a lily pad numbered 1 more than a multiple of 4, it remains on 1. So we're not going to really want to think about that anyway, so that suggests dividing the problem up into these 4 numbers. Also, the jumping move makes sense with these numbers as well. So each jump affects 4 lily pads in a row. It removes a frog from 3 of them, and it adds a frog to the 4th. That means that every time we make a jump, the parity of the number of the frogs on each class of lily pad changes. So for example, if we have a frog on a lily pad that's numbered 4 and we jump to the right, we remove a frog from 4, 5 and 6 and we add a frog to 7. So that changes the parity of all 4 numbers, and any jump will do this. Now let's see how we can use this to finish off the problem. So the remaining cases 8k plus 5 and 8k plus 7. If n is 8k plus 5, then we start with 2k plus 2 on lily pads that are 1 more than a multiple of 4, and that's an even number, and we start with 2k plus 1 on each other class, and those are odd numbers. So we start with an even number on 1 more than a multiple of 4, and an odd number on all the other classes. We're also going to want to make 4k plus 2 jumps, because each jump removes 2 frogs, so we want to end up with 1, so this is half of this minus 1. And that's an even number. So if we were able to make 4k plus 2 jumps, then the fact that this is an even number means we change the parity of each of these numbers an even number of times, which leaves them back how they were. So we end up with an odd number for n2, n3 and n0, and an even number for n1. But that's inconsistent with having just one frog remaining, because there are 3 of them which are odd numbers. So that proves that 8k plus 5 is impossible. Similarly, we can analyse the case 8k plus 7. Now in this case we have 2k plus 2 frogs on lily pads whose numbers are 1, 2 and 3 more than a multiple of 4, and only an odd number on lily pads that are 0 more than a multiple of 4. So the starting arrangement looks like this. This time, however, we have to make 4k plus 3 jumps if we want to be left with only 1 frog. And that's an odd number, so we're going to change the parities an odd number of times, which is going to leave them all flipped. So we end up with an even number for n0 and odd numbers for n1, n2 and n3. And again, that's not consistent with there being just 1 frog remaining, because there are 3 classes that have an odd number of them. So that also proves that 8k plus 7 is impossible. Now, technically speaking, this finishes off the problem, but it is interesting to ask what happens if we do the same analysis for the cases we now know to be possible, which are 8k plus 1 and 8k plus 3. If we start with 8k plus 1 frogs, then we have 2k plus 1 here, which is an odd number, and even numbers everywhere else. And we make 4k jumps, and this leaves the parities unchanged, so we end up with an even number n0, an odd number n1, and even numbers n2 and n3. Now, this tells us a little more than we knew, namely, if we start with 8k plus 1 frogs and we end up with only 1, we know that that 1 frog will end up on a lily pad whose number is 1 more than a multiple of 4. Similarly, if n is 8k plus 3, then we start with an even number on n0 and odd numbers n1, n2 and n3. We make 4k plus 1 jumps, which is an odd number, so it changes all the parities. So we get an odd number n0 and even numbers n1, n2 and n3. And that tells us more than we knew again. If we start with 8k plus 3 frogs and we end up with just 1, then we know that that frog will end up on a lily pad whose numbers are multiple of 4. So this method tells us something that we didn't know already.